Hey, sorry, like the computer started glitching and it restarted everything. So that's exciting. Sorry about that. Already with computer errors. Not sure what that means for the recording. So we'll get started in just a second. Trying to get this going. Let me know if there's any questions. All this setup. It's all good. Hopefully we're doing well. Hope you have a nice day. Midterm questions. So you just need to take it today at some point before midnight Eastern Standard Time. If you have not already, though, the majority of you have already taken. So I appreciate that. Let me I'm gonna share my screen in just a second. If you're in the meeting and don't have a question, then you just say hi or something, so it's recorded that you are here. No points, just for saying hi. So if you could do that for me. Okay. So any questions I should go over before I move on to new material? Yeah, the midterm is due today. It's the last day. Most of you have already taken it. So if you haven't, please do so. If you need to review for the midterm, please see previous lecture. That's what we did last week. Let's review. Silence my phone. No questions? Well, if there are no questions, I'm going to go on to new material. And the new material is we're going to start using the derivative to evaluate functions. So not just what is the derivative, that kind of thing. That's what we studied before. But now we're going to actually use the derivative to study the functions. What are we going to study? Well, the derivative can tell you about the rate of change of a given function. And that means it's kind of like the slope at any given point. You might want to know. So we can look at a function's derivative, as long as we can find it, as long as it exists, we can see where it's increasing or decreasing by setting it up correctly. And then we can also see at which points that it goes from either positive or negative or zero or undefined. You can see that. Another major portion of today's lecture will be going over asymptotes, which is review. We just need to remember how to find those. We're going to look at some asymptotic functions. We can still find the derivative of them as long as we're more specific about the domain. This will be more so in part B. So after the break, we'll look at those functions. Okay. As far as homework goes for this week, it's the standard 2 homeworks, 2 quizzes, normal thing. And then I'll just warn you that the second homework took me a lot longer to do than the first homework. So maybe map that out. So if you finish the first homework in an hour, you might double that for the second homework. Okay. It's very repetitive. There's a lot of parts. I'll kind of warn you about that. So yeah, well, we'll get into it and we'll talk about how we can speed things up if necessary. Okay. So looking at 5A, we're in chapter 3 now in the book. I think we don't even have to look at the book. We can kind of just understand what's going on. Do I have the right sheets? Says you can see it. Okay. I must have done some updates while we were gone. Okay. Number 1 says draw a graph to match the description given. F of x is increasing from negative infinity to -5 and decreasing over -5 to infinity. Okay. This is like algebra 2 stuff. So this is very basic. It should be very simple, especially if you're picking the graph from there. That's particularly simple. F of x is increasing. That means slope is positive. From left to right, it's going up. And from -5 to infinity, it's decreasing. Okay, well, we can see the correct choice. Here I have the parabola. Why is that the correct choice? We can talk about that briefly. Why is this the correct choice? Well, it's saying it's increasing. So it's going up from -infinity to -5, decreasing from -5 to infinity. So at some point it hits 0, right? We know that. When we get into actual functions given, we can talk about how we take the derivative and find that. But really I think it's the first 12 questions, you're just picking the graph. It's fairly simple to do. Skipping right along, draw a graph to match the description. All I have to do is pick it. Which of the following graph matches the description? It's decreasing from -infinity to -2 and 8 to infinity, but it's increasing from -2 to 8. You can see which one I picked. A here. Why is that true? It's decreasing this way. It's increasing going this way, decreasing going this way. You can see you have that change. Fairly simple to do, but you're just checking. All right, what does that have to do with calculus? What does it have to do with what we're learning in this course? Well, what we're going to do is we're going to find this. At first in the homework, it's given to us. Here's where it's increasing. Here's where it's decreasing. And in future problems, we'll look at finding those. So they'll give us a function. We'll take the derivative and we'll find where is this increasing, where is this decreasing. Okay, so that's the idea. But there's nothing really to compute. It's just understanding what increasing and decreasing. Number 3, g of x has a negative derivative over -infinity to 5. That means that its slope is negative. It's tending towards downward. G prime of x is less than 0 on this interval, and g prime of x is positive over this interval. Well, you can see I chose B. Why did I choose that? Because it's going downward from -infinity to 5. It's going upward from 5 to infinity. At 5 itself, it would have been 0. At 5 itself. We'll talk more about this later, but since I have a parabola right here, did you learn, you can say yes or no, I would appreciate participation. Did you learn up or down for parabolas? Do you remember that? Yes or no? Do you remember hearing that before? Maybe? No? Okay, we're gonna go over that, but this is up. Okay? So this parabola is up, and the way I'll remember that, it's up is a cup. Up is a cup. Right? Down is a frown. Up is a cup, down is a frown. That'll be important to us when we have to decide that, which we do in the homework. I teach it in pre-calculus, but it's possible it kind of came and went when you took it. All right, this is number 5. F of x has a negative derivative of negative infinity, or on the interval negative infinity to -2. F prime of x is less than 0 on this interval and this interval, and it has a positive derivative this interval and this interval. We have 4 intervals we have to deal with. Okay, see which one I chose. Why did I choose it? From negative infinity to -2, we are going downward. And then also from 4 to 9, we are going downward. From -2 to 4, we are going upward. It's just understanding. Negative means going down, positive means going up. Of course, these are synonymous with our everyday English that we use. Up, positive, down, negative. So it's just picking out the graph. Any questions so far about it? It's fairly simple. I think the next one I wanted to look at, let me peek at 7. I think the next one I wanted to talk about was 8. But let's look at 7. Draw a graph to match the given description. F of x has a negative derivative over these 2 intervals. Okay. F prime of x is negative over those intervals and positive over this over that interval, and the derivative is equal. F prime of x equals 0 at x equals -6. Okay, that tells you that it's going to either have a maximum or minimum. You can see which one I picked, and hopefully by now you can tell why I would pick that. It helped me. I had to maximize this and actually take a look at the points. It's, it's just picking the graph. I didn't have to draw it by hand. Some classes, some versions of this class, you have to do this stuff by hand. We don't, because we're kind of a hybrid class here. Hopefully it's simple enough to see. All right. Okay, so that's the first chunk. It's pretty easy because you're just picking the graph. You don't have to draw it yourself. Drawing it in the computer or on paper, the other 2Ds. So skipping right along to problem 8 is where we get to start doing some actual work. Part A, find the critical values, and part B, find the the relative extremums. What is this talking about? All right, in the previous examples, we saw that we had positive slope, negative slope on this interval. How do you find those? Where does it change? How do you do things like this? Okay. The way we're going to do this is we're going to take the derivative of the function that they give us, and we'll set it equal to 0. If we do that, then we'll see where it changes, okay, where it's going to change. Because if it's flat, and if it's normally curvy, but if it goes flat at some point, it must be changing from either going negative to positive or positive to negative. Okay, that's the idea. We're finding the bottom of the hill, the valley, or the top of the hill. That's what we're going to find. So this one's easy enough. I'm sure your version is easy enough too. We just take the derivative. So that would be 2x minus 4. Okay. So I'll set that equal to 0. So f prime of x equals 0 gives me 2x minus 4 equals 0. Implies that x equals 4 divided by 2 is 2. So in my numbers, I get x equals 2. Okay. That's where this occurs. That's where it occurs, at x equals 2. Okay. What is the value at x equals 2? F of 2, or, you're going to have different numbers, but the idea is the same. Okay. So what's that? 4 minus 8 plus 2. -2. Okay, so we have f of 2 equals -2. So that's the value. Switch colors. Kind of annotate this. That's the value. That's x equals 2. That's where it occurs. So the critical values of the function is R2. Okay. It's at x equals 2. What's the relative minimum? Well, why is this a minimum? Because this is a parabola. This is a parabola. So this is occurring at 2. Okay. So it's occurring at this value, f of 2, where we found f prime of x equals 0. Solve for x. They're calling this a relative extremum. Okay, why? Because that's a minimum point. This is a parabola. Parabola, when you do that, you find the minimum value. Parabolas either have a maximum or a minimum. Okay. So that's the idea. That's the, when I think back to what I learned when I was in this class, when I was learning calculus, the thing I had memorized is you take the derivative, you set it equal to 0, you solve for x. Take that x and you plug it back into the function, that gives you the value. I don't know if I really understood what it was I was learning, but I certainly memorized you have to do that for the exam. Okay, so that's the idea. Take the derivative, set it equals 0, solve for x. That tells you where it happens. Plug it in, that tells you what's occurring. That's either the maximum or minimum. All right. Now, since this goes to negative infinity to positive infinity, that's going to be an absolute minimum. Okay? That's the minimum of the function. But other things can be kind of curvy, and they can have relative minimums, relative maximums. Right? If you think of a business, there was good times and bad times, that kind of thing. And, the absolute minimum might be 0 or in debt, or maybe the absolute maximum is to infinity. We'll talk about that. But you can have relative maximum. That's the idea. Let's take a look at 9. And this should be just about the same problem. There is a lot of repetition in this homework. So looking at question 9, we have g of x equals negative x cubed plus 12x minus 10. G prime of x then equal negative 3x squared plus 12. If I set that equal to 0, g prime of x equals 0. Now, why am I doing that? I'm going to solve where the slope goes 0. Okay, that will tell me that there's some kind of critical point there. So that's why I'm setting it equals 0. Now let's actually do that. 3x squared plus 12 equals 0. Okay, and then now we're in elementary algebra. Hopefully I don't make a mistake. 3x squared equals negative 12. Negative 3, let's go back. X squared equals 4. X equals root 4 plus or minus. X equals plus or minus 2. You have to remember that old algebra rule. If you take the square root of both sides, you have to do plus or minus, because you could plug in negative 2 squared equals 4. So we get 2 values for this. 2 values for that. Now, where does this actually happen? Oh, I'm sorry. That's where it happened. Once you plug that in, what are the values? Okay, what are the values? So if you plug in negative 2, you get negative 2 cubed plus 12, negative 2 minus 10. Looks like I got negative 26 for my numbers. And then also plug in your other value. For me, it was positive 2. My numbers, I get 6. Okay. That is the idea. Relative minimum, relative maximums. For some functions, you can have an absolute minimum or an absolute maximum. You also have relative maximums. Okay. If you think of a field, it can have hilly parts and lower parts, that kind of thing. Even if it's on average flat, that's what we're thinking of here with our functions. So what do? You take the derivative, you set it equal to 0, and then you solve for x. Take that x and plug it back into the function. Maybe you get more than one x, so you plug in more than 1. So that tells you where it occurs and what occurs. That's the idea. What to do, why to do it. Okay. Let's get to now. The homework is very repetitive, but it's good. You have to. You do have to practice it. All right, in this one, which is, and you'll see what I mean by all the parts. This is Prop 11. Find any relative extrema of the function. List each extrema along with the x values at which it occurs. Identify intervals over which the function is increasing or decreasing. When it is decreasing, sketch the graph of the function. Luckily, we just have to make it. We don't actually have to sketch it. So that makes it quite a bit easier. All right, what do you think we ought to do? Well, if we're going to find these extrema, we're going to take the derivative. Move this down a little bit. That would be swell. G prime of x equals -3x squared plus 8x plus 16. So I'm going to set that equal to 0. That'll tell me where it occurs. It looks like I'm going to get 2 answers here. Let's see what happens. So G prime of x equals 0 tells me where the slope equals 0. So that's -3x squared plus 8x plus 16 equals 0. It's a quadratic. Hopefully we can do that. We can either do this by, there's so many different methods to solve a quadratic. We could try factoring. I know that 3 and 16 don't have anything, so we can't factor out the 3. And then that leads me to AC method. And I could try to do 3 times 16 and then find it, or we just use the quadratic function. I think I'll just go straight there if there's no objection. Have we done quadratic function yet in this class? Just in case, minus b plus or minus root b squared times 4ac over 2a. I don't know if I've ever written that down for you, but that's one to know. All right. If that's the formula, I guess this would be -8 plus or minus 8 squared minus 4 times -3, 16 over 2 times -3. That ought to do it. I need to check on that arithmetic here. 8 squared minus 4 times 8 squared minus 4, -3, 16. -8 plus or minus 16 over -6. That's equals -8 minus 16 divided by -6. I got +4 for my numbers, and -8 plus 16 divided by -6. Get -4/3. Okay, this is where it occurs. This is where it occurs. What occurs? That is where the slope is 0. Okay. Now, if the slope is 0, sure, but what are the actual values? What are the actual values? That's where you plug it in. Okay. Let me switch colors to remind myself that's what I'm doing. So now I'm going to go f of -4/3 of the original function, and this will tell me where we are. So -4/3 cubed plus 4 -4/3 squared plus 16 -4/3 plus 9. And like I got -77/27, my numbers. And then f of 4 is -4 to the third plus 4 times 4 squared, 16 times 4 plus 9. 73 there. So this tells you what the extremes are. So that's the relative minimum, relative maximum. This is the max. This is the min, relative. Relative. So what are you doing? You're finding the top of the hill, the bottom of the hill. Top of the hill, bottom of the hill. How do you do that? Take the derivative, set it equal to 0, solve for x, plug those x's in the original function. And that tells you. Another way to do it is to graph the function. You can graph the function and you can see where this occurs. I'll get to graphing later. I already have my graphing calculator pulled up. And on some of those, I'll do those as well. You can do that on any of these though. Okay. Let me move down because it looks like there was other parts to the question. To answer everything. Increasing, decreasing. Okay. How do you find that? How do you find where it's increasing, decreasing? Let me write something down and then I'll clear my screen. So we found f 77/7 was our min. F of 4, 73. This was our max. Let me get rid of some of this. How do you find increasing, decreasing? There's the easy way, the really easy way, and the hard way. So increasing, decreasing. Let's first talk about the hard way, which is the way the textbook would tell you, right? So what is increasing? The derivative, that means that the derivative is positive. So the hard way would be to do something like, okay, -3x squared plus 8x plus 16, which is the derivative, set this equal to 0, and then solve the inequality. And that to me, that's absolutely true. That's if I was writing a textbook, that's what I would say. Set the derivative greater than 0 and solve. But in a practical, trying to solve all these homework problems, what can you do? Well, you know where it changes. You know where it changes, right? You know that, okay, I have 2 points in which the derivative is changing, okay? So I have my 2 points. What can you do? you can just plug in a point in the derivative and you can see if it's positive or negative. So that would be the other way, as opposed to solving the inequality, which you are welcome to do, and that's what the textbook would tell you to do. If I was writing a textbook, that's what I would tell you to do. But another way you can do it is you can just simply plug in a point in the derivative and see what happens. So we know it changes at -4/3. You could just plug in f of -2 in the derivative and see, is that positive or negative? If it's positive, it's increasing. If it's negative, it's decreasing. And that would answer the same question. I would just answer the same question. Okay. And this is really easy to do in a calculator. Okay. That's really easy. You can just plug that in, see what it says. So if you just have a scientific calculator, this would be fairly easy to do. I find that this equals -12, which means it is decreasing. Okay, so that's an area it's decreasing. Okay, I claim that if it's decreasing just a little bit left to our transition point, it's transitioning from -infinity to that point. Okay, so that's where I can find out. Now, where am I? What about in between? And what about, let's pick a point that's in between. So all I have to do is pick a point between -4/3 and 4. How about 0? F prime. -3, 0 squared plus 8 times 0 plus 16. And that gives me +16, which is certainly positive, which means it's increasing. So here it is increasing. Here it was decreasing. Okay. And then I can pick a point after 4, about 5, and we'll see what happens. F prime of 5, -3, 5 squared plus 8 times 5 plus 16. All I want to know is this positive or negative? Don't even care what number it is. I just need to know, is it positive or negative? -35, which is negative, which means it's decreasing. What did I just do? So I'm trying to figure out, where is the function increasing, decreasing? I know where it changes. I know where this changes. It changes at that point and that point. That's where it's changing from either going positive or negative. So I picked a point that's a little bit left of that one. You can pick very left if you want. You can pick a -100, and I claim it'd be the same. Okay, so left of that, I chose -2. Why not? That gives me, okay, that was decreasing. So that means from -infinity up to our turning point here, this was decreasing. Then it flips. Okay, I know it flips because I just solved it, but I showed it to you. Now it's positive. So between this point and this point, it's positive. And then after that point, we know it changes. Well, it was positive, so it must be negative. But I showed here that yes, indeed, it is negative. So I would say that's the medium way of solving this. Okay. The medium way. The hard way would be setting up the inequality and trying to solve. Here, I'm just plugging in points. I have to be a little bit careful. I have to kind of know what I'm doing, why I'm doing it, what I'm looking for. But it's very easy to compute. Remember, I am plugging in points in the derivative and not the original function to find increasing, decreasing. Just want to know, is it positive or negative? So that's medium level. Easy level, bordering on cheating, but easy level would be just to have the computer graph it and you can just look at it. That would be the easy way. And I'll show you that later, but there's not much to show. It's just looking at which way the graph is going. If you actually have to compute this, or God forbid you had to write a program to compute something like this, that's what you're looking for. Tell me if the derivative is positive or negative. That's the idea. It's a little confusing when you first look at it, but it really is dead simple if you know what I'm talking about. I mean, you're just plugging in numbers. Any questions, comments, or concerns? Are there anything you'd like me to do again for this problem? Did you have a similar version of that? Mm-hmm. Yeah, okay. Okay. I personally think it's easy to just plug in. You have to kind of know what you're doing, but just plugging in points in the derivative, since we're just dealing with polynomials, it's pretty easy. Trig functions, it gets a little trickier, but that's 13. It's roughly the same thing. This is very repetitive, but that's good because you have to kind of drill it into your head what it is you're doing. Find the relative extreme points of a function if they exist, then sketch a graph of the function. Okay, so I'm going to take the derivative. F prime of x will be 3x squared minus 27. Okay. I'll set that equal to 0. I'll solve for x. X squared then equals 9, which implies that x equals plus or minus 3. So that's where it occurs. Now I'll plug those 2 points in the original function and find what are the values. That should tell me relative min, relative max. So f of -3 is -3 cubed minus 27 times -3 plus 53. And for that, I got 107, which is my relative maximum. And then f of 3 cubed minus 27 times 3 is 53. I got -1, relative minimum. Took the derivative, set the derivative, first derivative equal to 0. Solve for x, plug those x's into the original function. That tells you the values. Whichever one's bigger, that's the maximum. Whichever one's smaller, that's the minimum. Now, if you want to find the increasing, decreasing, since we have 2 points that split it, you can just cut it here and you say -3, 3. So you have this region. Let's call it 1, 2, 3, and you can find where it's increasing. And again, that's something that we go over in pre-calculus. I remember learning it as a student. I know I teach it as a professor. So hopefully you've gone over it, but of course you'll have to refresh a little bit. It's not too bad. And then since this is an online course and you can use a graphing calculator, you might as well. You can just graph the original function, find it's increasing, decreasing, and this makes picking out the graph completely trivial. And if you're going to use a graphing calculator, you might as well use Desmos, right? I mean, Desmos is pretty awesome. So I would suggest that if you're using a graphing calculator, you might as well use a good one. So I would check out Desmos. It's 13. We're about 22. I want to say 15 was interesting. Oh, it's a word problem. That's why I have a highlight. Okay, the temperature of a person during a certain illness is given by the following equation. Or capital T is the temperature degree Fahrenheit at time T in days. Find the relative extreme points and sketch the graph. Sketch a graph of the function. Okay, so we just need to find where the relative maximum or minimum is occurring. I do notice, and this might take a little bit of refreshing. You notice that this is a parabola. You notice that the A term that we talk about with ax squared plus bx plus c, or the general quadratic. A is negative in this, which means you have a parabola that looks something like that. Okay, so I know it's going to be a maximum just because of that coefficient. You may not have looked at that in a while, but I've taught it many times, so that's at the forefront of my mind. So that's good to know, because now I know just by the coefficient, just by that number of negative 1/10, I can just see, okay, this is going to be maximum. All right, so let's find that maximum. I think we should find T prime. T prime of T. So that's going to be negative 0.2 T plus 1.2. Did that right? And we're on the domain positive time up to 12 days. So we don't want to go past that. All right. So there we have it. Now, let's set that equal to 0. T prime of T equals 0. Applies negative 0.2 T. It's 1.2 equals 0. Right. 0.2 divided by 0.2. T equals 6 days. So that's where the critical point is. That's where it changes its orientation. And we see that as 6, okay? So that's 6 days. Now we can see what is the temperature at that. Plug it in the original function. We've got 102.3 degrees Fahrenheit is the maximum temperature of this patient. That's a word problem, nursing problem, I suppose. Does it make sense what I'm doing? Is it clear how to do it? If you take the derivative, you set it equal to 0. Solve for x, that tells you where a critical point, it doesn't, it just tells you where it occurs. Plugging it into the original function gives you either the maximum or minimum, at least relative. So that explains part 1. Part 2, sketch the graph of the function, choose the correct, you can just plug that in to a graphing calculator if you choose. I knew it was upside down parabola. So too big of a deal. Any questions on how I'm getting this? That was 15. Next one I wanted to talk about. Now I need to go over. Let's see. Let's see what 17 brings. I can't remember if it was interesting. Yeah, I do want to talk about 17. I'll say it's not necessarily this problem, but this idea that I'm going to go over, heavily tested, not just in our class, but when I took the GRE, this, like for math, this was all over it, okay? Is it necessarily more important than one thing or the other? No, but it's heavily tested. Maybe it's just an easy question to ask. What is it I'm on about now? They give you the graph of the derivative and they're asking you questions about the original function. This is heavily tested. It's possible you even saw this on, if you took ACT or SAT, if they have calculus questions on there, it's possible you would have seen it there as well. It's heavily tested. So the graph of the derivative is shown to the right. We'll have to pull that up. Use the information in the graph to determine where f is increasing or decreasing and the x values are the extrema. Then sketch the graph if possible. Okay, this is always a heavily tested issue. This is the graph of the derivative. This is f prime. This isn't f of x. All right, we see that the derivative is a line. Okay, cool. It looks like it's negative. The derivative is negative from here to here. Okay. In my numbers, what is that? So for my numbers, that's at -10 to 987. Looks like -7. The derivative is negative. Then it hits 0 at 987. Okay. So f prime of x equals 0 at x equals -7. Then it's positive f prime of x is greater than 0 from -7 to infinity. Again, this is the derivative of, this is the graph of the derivative, not the original function. Not the original function. Okay, so from that information, let's see if we can answer some questions about what's going on. Where is the function increasing or decreasing? Okay, well, the function was decreasing from -infinity to -7. We saw that. Decreasing. It's talking about the original function, not the derivative. So you have to see, where is it negative? Where was the derivative negative? From -infinity to -7. Where is it increasing? From -7 to infinity. Positive. The derivative was positive. What the x values of the relative minimum? We saw that the derivative was 0 at x equaled -7 for my numbers. Okay. Wherever it hit 0 on that graph, the x-intercept for the derivative. Okay. What's the relative maximum? We didn't have this. There's no relative maximum for that. And then what is the original function? This is heavily tested in the curriculum of the United States. Why do I say it's this? Okay, it was, slope was negative, and it even has the same dot right where I did it. There's the slope is negative, okay, up to that point. Slope is negative, derivative is negative, and it switches to positive at that point. This is the original function. This is f of x. This is f of x. I think one of the reasons why this is heavily tested is it's fairly deep-rooted in actual calculus, not just pre-calculus. There's not much computation that goes into it. Like, there's no formula I need to understand. There's no, there isn't much computation. You just have to understand what's going on. So it's a little bit more logic rather than just heavy computation. So I think that might be one of the reasons why it's so heavily tested. But I've seen that question a million times, different versions, of course. It's not just this one, but that type of thing, it shows up all the time. Are there any questions? That was number 17. I want to say, let's look at 19. I want to say that there's one pretty close to it. Yeah, let's, instead of 19, let's do 18. So 18 says the graph f prime is shown to the right. Use the information in the graph to determine where f is increasing or decreasing the x values of the extrema, and then sketch a possible graph of f. Okay. So the derivative is a parabola. Okay. Where is it negative? It's negative. What looks like it's just going to keep going to me. Looks like it's going to keep going. So f prime of x is less than 0. I'm going to guess negative infinity to what looks like -1. That's where it looks like it's negative. Then at x equals -1, we have it equals 0. F prime of x equals 0. That's important to note. Then it's positive. F prime of x is greater than 0 from x between -1 and 1, 2, 3. Then it hits 0 again. X equals 3. We have f prime of x equals 0. And then it's negative. F prime of x is negative from 3 to infinity. So just I'm making some notes to myself. This is what seems to be happening with the function. So again, this is the graph of the derivative, not the graph of the original function. Going a little bit higher than what you're expected to understand. But if the derivative is a parabola, what do you think the order of the function would be, the original function? If the derivative is a parabola, take the derivative of something, you get a parabola. That's x squared, right? So what was the original function? It must have been x cubed. I mean, we can assume, right? Okay. So from there, these are my notes. Where is the function increasing or decreasing? Okay, well, you can see why it's decreasing from -infinity to -1. Okay, we got that right here. And also from 3 to infinity. So I had that in my little notes to myself. It's increasing from -1 to 3. Right here. What is the relative minima that occurred at x equals -1? You can find that by plugging it in the original function. And so that means the relative maxima occurs at x equals 3. That's where the derivative equals 0. And you can find, well, what would be the original function? And again, I'm trying to hint towards it. But if the derivative of x equals ax squared of some type, then f of x would have to be some kind of a cubed. It would have to be. So I knew I was looking for something with x cubed. You can just figure out from decreasing, increasing, and where your critical points are. Fairly easy to tell from that. Questions?
Can you scroll back up to?
I can. Which part?
Just the first part.
First part. That's where I found the increasing, decreasing. And to do that, or how I did that.
I just wanted to see how it worked.
if I can find it. Here's my notes. Yeah. Comma between there. That can be tricky. Of determining how does MATLAB want this answered. That's also. I will fully say I teach the course. I'm pretty good at algebra and calculus. I'm so at predicting what MATLAB wants it answered in the style of, as you can see of me teaching this. That to me is the hardest part of this course, is figuring out how does it want to answer. Does it want a comma or does it want a union? That can be tricky. So I still look at view and example sometimes. I'm like, how did you want this answered if that's not right? So yeah, I would always utilize that. It usually gives an example of how the style. So that's how I do it. That's how I figure it out. And then, God forbid, I'll get it wrong, and it'll be like, the correct answer was this. I'm like, you wanted it that way. You win this round, computer. Okay. That was 18, but I think it's a good one. I would keep that. Let's see, we're at 2 o'clock. For the graph shown, identify the points. Inflection points. Okay, this is, we can just briefly talk about this. So just from graph, what are the inflections? Well, it seems like something's going on right here. Something's going on right there. Okay, so it's changing its direction, right? It's changing. It was negative, and then it became positive. It's positive and goes negative. Okay. So something happens at that point. What is it? Well, slope goes 0. Yeah. That's a relative minimum. Okay, this would be a relative maximum. If you asked me where is that point, well, I can tell from the graph. Looks like it's -2, 4, and 0, 6, 7, 8, 0, 8. Okay, that's where it's occurring. So those are the inflection points. What else did it ask me? Identify where the function is concave up, concave down. So we briefly talked about that, but now we should really talk about it. What is concave up? What is concave down? If you're making a cheat sheet for yourself, this one goes on there. It's not hard, but it should go on there. Up is a cup. Okay. That's your U-shaped. That's up as a cup. That's your U-shape. That is occurring here. Okay. Hopefully you can see that. We have that parabola at that shape of a cup shape, right? Up as a cup. Down is a frown. Down is a frown. Where does that occur? That's occurring here. A downward turn. Okay. We have a little frown there. Up as a cup. Smiley face. The good thing is, our English, well, I'll say American idea of up, positive, smiley face, all consistent. So it's very easy to remember. Okay, smiley face, up, positive. Down, negative, frown. Okay, at least all those line up with each other. Those all make sense. So if you're looking at the function, where is it up? Well, where is it like a cup? It's like a cup here. So I'd say from -infinity to 0, it's like a cup. Where is it like a frown? From -2 to infinity, it's like a frown. So let's talk about how you enter that in. The function is concave up from -infinity to -1, and concave down from -infinity to infinity. So up is a cup, down is a friend. That's how you can determine that. Where is that coming from? Let me explain the actual calculus rather than just teach you the homework. Think of f of x equals x squared. Okay, that's a parabola. That looks like this, right? Take the derivative of this, f prime of x equals 2x. That's the derivative. What's the second derivative? 2, which is greater than 0, which is positive. Okay, up is a cup. Second derivative will tell us the orientation, but we don't need to do that if we know the graph. But we will for the second homework. Okay, let's say let's switch. G of x equals negative 2x squared. What does that look like? Looks like this. Down is a friend. Take the derivative. G of x equals negative 4x. Second derivative, negative 4. Down is a friend. Less than 0. So the second derivative will tell us that. If we have the graph, we don't need to do all that. We can just look at it. But if we need some way to compute it, we can find it in this way. So up is a cup, down is a frown. Second derivative is positive or negative. That will tell us. And where that occurs, the points, we can set it equal to 0, the first derivative equal to 0 to find that, which is what we've been doing. Okay. That was 19. Now I need to skim right along. Maybe the question. Let's get to 26. Person coughs with an object in their windpipe. The velocity of the cough depends on the size of the object. Suppose a person has a windpipe with 14 millimeters radius. If a foreign object has a radius r in millimeters, then the velocity v in millimeter/second or millimeters per second needed to remove the object by a cough is given by the following equation, where k is some positive constant. For what size object is the maximum velocity needed to remove the object? So k is just some real number. K is greater than 0. So we don't really need to worry so much about k. Okay. What is the maximum velocity? That sounds like we need to find the relative maximum of some kind. How have we been doing that? Take the derivative. We set it equal to 0. We should be able to find it. Okay, so let's do that. I might rearrange the know if I absolutely need to do this, but just being cautious. And rearrange b just to be sure. Taking the derivative is easy stuff, hopefully. All right, I bring down the 2, so b prime r 28 kr minus 3k r squared. That's the derivative. If I set this equal to 0, then I should be able to solve for r. B prime r equals 0 gives me 28 kr minus 3k r squared equals 0. So from there, I can do a bit of factoring. Looks like I have an rk for both. 28 minus 3r (0), which implies that r either equals 0 Or 28 equals 3r, r equals 28 thirds. I don't think the radius is 0. So it's 28 thirds millimeters. Enter as an integer or simplified fraction. That's what we did. Have it. So what is the size? For what size object is the maximum velocity needed to remove the object? Radius of 28 third millimeters. We'll need maximum velocity to remove it. Okay. So that's 26. Let's take a peek at 27. Let's see what we need to do. All right, 27. The number of visitors P to a website in a given week over 1 year period is this function where T is the week 1 to 52. I think that is actually my note. I think I messed up when I first tried this. Over what interval of time during the 1 year period is the number of visitors decreasing? So you just want to find P prime of T. Yeah. Where is it decreasing? So you can find where is this less than 0? Where is it increasing? P prime of T is greater than 0. Where are the critical points? Critical point means the number of pairs minimized at 38. Yeah. Okay, I think it'll be okay. Since I'm over on time, I think that should be good. I think you'd be able to take the derivative as long as you followed the past 2 lectures of how to take the derivative. If you followed this, you should be able to take the derivative, set it equal to 0, and then find where it's increase, decrease. If that fails, you are more than welcome to just graph the function itself. You can graph the function itself and then find where it's increasing or decreasing. Just note that you're over this time interval, okay? And I'll take a picture of my answer so you can always peek at that. But that's the idea. So you can always just graph the original function and see what's going on. That can make it quite a bit easier too. Okay. All right, if there are no questions, I'm going to take a 10-minute break. We'll come back and we will get into part B, which is kind of the hard stuff. Okay. And I'll be back in 10 minutes. You are back. Just say hi. It's pretty low intent. That's okay. Glad you're here. Just give me a hi that you came back. And we'll get started. Um. The next section, part B. I think the hardest part, again, is pre-calculus, not necessarily the calculus of it. I'm gonna try to show you where you can speed things up. I might use the graphic calculator a bit more for this one, because technically we've learned the last section, so we can use all of that we learned. We don't have to start from scratch for this. And also with the pre-calculus of it all, this is something we should have learned once. I have a feeling if I review it, it'll come back to you. And of course, since we're allowed to use graphing calculators for this, we might as well, right? And a lot of this is going to be asking you about graphs, and that's actually the hardest part, is being able to do this without a graphic calculator. But you can use one, so we might as well. But a lot of it's going to have to do with asymptotes. Do you remember what an asymptote is? If we think about a limit or something, it's where all of a sudden the graph is shooting off to negative infinity or positive infinity, and the graph is just breaking. Matter of fact, let's look at the graph right now together and just talk about what asymptote looks like. So hopefully I'm projecting this. So if I just have y equals 1 over x. This is the classic example here. What's happening is that at x equals 0, we have this break here. So from negative infinity going to 0, we were coming along, and then all of a sudden we shoot down to negative infinity. And that's because the function can't actually hit 0. We don't have a definition of what it means to hit 0. So 1 over 0, we don't even know what that means. So the graph is just shooting down to negative infinity. Then right after 0, if you can, think of our limits, right after 0, as close as you can be to 0, but just a little bit to the right, it's going from infinity down, 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 down. And eventually it'll be asymptotic to y equals 0. So we have two asymptotes. One is vertical, and that's, I'm going to say, the more important one. The more important one is that we can't divide by 0. We don't even have a definition of what that means. So we can't divide by 0. That's happening at x equals 0. We also have a horizontal. I'm going to say it's not as important, but it's kind of important. X equals 0 right there. That is our vertical asymptote, and that is occurring because we can't divide by 0. We have a horizontal asymptote because of this, y equals 0. So that means this function is not going to, it's not going to touch the graph. Now, if you take a pre-calculus, I know with my course, we spent a full week on finding asymptotes. Maybe 2 weeks, a week or two on this. So it's something to review. For you guys, you've technically already learned it, so you just have to remember it. And the thing I would tell you is to find a good cheat sheet to remember this. Okay, I have one pulled up for us that we can peek at. Of course, the textbook goes over it, but it's all about just knowing where this is occurring and then also referring to the graph. Okay. Okay. So looking at question 1. It says determine the vertical asymptotes of the function. If none exist, state that fact. Vertical asymptotes, that was where x equaled 0 there. Okay. So it's what number can x not be, really is what I'm asking myself. Looking at this denominator, x minus 7 cannot equal 0. Where does that occur? That occurs at x cannot equal 7. So that's a vertical asymptote. So the function will avoid that occurring. It will avoid that occurring. So the function has one vertical asymptote. That is x equals 7. Or whatever yours is. It's just where the denominator is hitting 0. Skipping along, it's the same idea, but now it's quadratic. So the function f of x, 5x over x squared minus 25. When I say quadratic, I mean denominator is quadratic. Where's the vertical asymptote happening? Well, x squared minus 25 cannot equal 0. I can solve where that occurs. X squared cannot equal 25. Where does that happen? X cannot equal plus or minus 5. It means we have two vertical asymptotes occurring here. Two of them. X equals -5, x equals 5. Three. Determine the vertical asymptote of the following function. If none exists, state that fact. Well, I just can't have this denominator equaling 0. So x squared plus 8x plus 12 equals 0. Where does that happen? Is it possible for me to factor this? 3 and 4 don't add to 8. 2 and 6 do. 6 and 2 multiply to 12. So x plus 6, x plus 2 equals 0. So x cannot equal -6, -2. Now, why does it say the function has one vertical asymptote there? Go into the original function, f of x, x plus 2, x squared plus 8x plus 12 is x plus 2, x plus 6, x plus 2. What happens is it reduces. So you get 1 over x plus 6. So you see x cannot equal -6. So then you'd be dividing by 0. So it only has 1 because of that reduction. Oh, algebra trick. That one technically only had 1. Moving on to 5, which I think is similar. Yeah, it is. Determine the horizontal asymptote of the function. If none exists, state the fact. Which one was the horizontal? That's left to right, right? Okay. So for this part, I'm going to pull up the cheat sheet and we're going to kind of go over it together. If this was a normal class, we'd have a big long lecture. I'm just going to pull up the cheat sheet and talk about it. So I can post this with the notes. I'd be happy to. I didn't write this, by the way, but I think it's pretty good. Vertical and horizontal asymptotes. So tells you what they are. We just saw this reduction rule. I'm hoping I'm projecting this. Yeah, okay. I can post this with the notes, I think. F of x equals x minus 2 over x squared minus 4. That's very similar to the problem we just worked on. You see it's 1 over x plus 2. This means that the graph f of x has a hole where x equals 2. Okay. The graph, exactly 1 point, x equals 2. Graphing calculators will not show the hole in the first graph, but the table will show an error when x equals 2. So that's important to note. If you plug this on Desmos or something, it's not going to show that. So that's kind of where our theory is more, these things aren't perfect because of the methods they use, so that's not going to show it. But the idea with vertical asymptotes is that there's certain numbers that are not in the domain of the function because we can't divide by 0, of course. Now, we want to really talk about horizontal asymptotes. These are the hard ones to remember, and this is, I would have maybe something to write your own cheat sheet, that kind of thing. But it's hard to remember, but it's easy to understand. Horizontal asymptotes, this is where we want to see where that, with 1 over x, we saw it was y equals 0, and it will be for a lot of them. So case 1 says, the result has no variables in the denominator. The function has no horizontal asymptote. Okay. So the example is x squared plus 1 over x minus 3. Go ahead and cancel those constant terms. X squared over 2x. You're looking at x over 2 with the reduction. There's no horizontal asymptote, and you can see an example there. Case 2, if the result is a number, the horizontal asymptote is y equals that number. Okay. So for b of x here, we have 1 minus 6x over 3x plus 7. Cancel the constant terms. We don't care about those because we're going out to infinity here. Negative 6 over 3, you're just looking at, really, what they should say is you're just looking at the ratio. So negative 6 over 3 is negative 2. So that's where the horizontal asymptote is going to occur. We'll see that in our examples. Case 3, if the result has no variables in the numerator and the horizontal asymptote is y equals 0. Another way that this is phrased is if the degree of the numerator is smaller than the degree of the denominator. I think that's how our book says it. That's how the textbook of my pre-calculus class teaches it. If the degree of the numerator is less than the degree of the denominator, that's going to occur. So think about if this goes out to infinity, if this goes to negative infinity, what's going to happen? These are the 3 cases that can occur. Okay. So again, notice the degree of the numerator is larger than the degree of the numerator or denominator. No asymptote. Horizontal asymptote, we can do that. And then the fourth case, I guess, is the slant asymptote. And I'll show you, it's in the homework, I'll show you which problems those are. Those are probably the hardest, but it will be okay. We'll get to it. Does it talk about slant asymptotes? I'm going to, but I don't know. I don't see it. That's okay. We're going. So those are your 3 cases. Over here. What do we have? F of x equals 8x over 10x minus 9. Those are the same degree. That's a degree 1. That's a degree 1. This is problem 5. They are equal. They are equal. So we just take the ratio. 8 over 10, 4/5. Y equals 4/5 is the horizontal asymptote. The horizontal asymptote. That's where it's going to occur. Okay, left to right. If we plug this in a graphing calculator, if we plug that in Desmos, you will see that that occurs. Y equals 4/5 is our horizontal asymptote. There's also a vertical asymptote for this, but it didn't ask. Is that okay, Kelsey?
I'm just writing on the first. You should.
Okay, I want to make sure. Two things. Let me see what 6 brings us. All right, now this one, the degree here is 1. Degree here is 2, which means the degree of the numerator is larger than the degree of the denominator. If that is the case, the horizontal asymptote is y equals 0. That's the idea. So because of the degrees, you have 4x over x squared. You roughly just have x over x squared. You have 1 over x. So as you go to infinity, the only thing that really matters is the degrees. And here we see it's turning into 1 over x as you go to infinity. As x approaches infinity. That's the idea. It's basically turning into 1 over x. So the asymptote will occur y equals 0. So it'll be asymptotic. Y equals 0. So it's good to have a little cheat sheet to remember these things. Let's see, determine the horizontal asymptotes of the function. If none exist, state the fact. For this one, I think it's kind of easier if I rearrange this a little bit. This would be equivalent to 3x minus 9 over x. That might be a little easier to see. So say totally equivalent. Totally equivalent. Just by algebra, moving things around a little bit. Now we can see, okay, as this tends towards infinity, this is going to be like 3x over x. So this is tending towards 3. So y equals 3. Because they're equal, it's just taking the ratio of the coefficients. C, yeah. All right, in this one, I see that the largest degree of the numerator is larger than that of the denominator. For me, I have degree 5 in the numerator and degree 4 in the denominator. What does that mean? There is no horizontal asymptote. That is the rule. Those are 3 cases, right? You can either have y equals 0, you have the ratio, if they're the same degree, you have the ratio, or you have the, if the degree in the numerator is equal to that, I'm sorry, if the degree of the numerator is larger than the degree of the denominator, we have no horizontal asymptote. So it's worth having those, and I can post that cheat sheet. It's one of a million cheat sheets out there with this. It's also in our book, but I couldn't find it like clearly, succinctly written down in our book. Maybe it's there and I just couldn't find it. But you have the 3 cases there. Case 1, if the degree on the top is larger than the bottom, no horizontal asymptote. That's the example we just looked at. Case 2, if they're the same, you just take the ratio of the coefficients. And there's your horizontal asymptote. Case 3, if the degree on the top is smaller than the degree on the bottom, then it's y equals 0. That is the idea. Questions on that? There's also going to be the case, which I do not see listed on this, where you can have a slant horizontal asymptote. Maybe that was 9. I can't remember. Oh, let's just look at this one. Here we have roughly 2x to the 5th, 4x to the 6th. So we have, this is smaller than denominator, so it's just y equals 0. It's a horizontal asymptote. It's tending towards 1 over x. So as x goes towards infinity, f of x is tending towards 1 over x. That's the idea. X is so large that the only thing that matters is the degrees at that point. Looking for my slant horizontal asymptote. Here we have 12x cubed over 20x cubed. Well, as x gets huge, this is really just tending towards 12x cubed, 20x cubed. Since those are the same, 12 20ths, 6 tenths, 3 fifths. So I think we have an asymptote of y equals 3 fifths. It's just a reduced ratio. Write anything down until problem 12, so it must be pretty easy. Determine the horizontal asymptote of the function if none exists. State the fact. Okay, so with this, what do you have? Y equals 0. Asymptote. But we've played with the natural exponential a lot, right? So we've seen this guy before. And what was the first one I need to note? So let's take a look at that. Sketch. Now, of course, when our homework says sketch, you are more than welcome to just plug it in a graphing calculator. So sketch the graph of the following function, indicate where the function is increasing or decreasing, where any relative extrema occur, where asymptotes occur, where the graph is concave up or concave down, and where any points of inflection occur, and where any intercepts occur. So it wants us to sketch a graph. Graph. We could just plug it in Desmos and have that sketch a graph. That would be easy enough. Or you can use your TI-84 if you please. -3 over -7. See what was vertical. Easy to see, we're going to have vertical asymptote x equals 7. There you go. It looks like the graph is increasing from negative infinity up to 7, but it never actually touches 7. And then from 7 to infinity, it's also increasing. That's kind of weird. So where is it decreasing? I don't think it is. Even though it's discontinuous, I don't think that's actually ever decreasing. So where is this increasing? Well, we saw from graph, negative infinity to 7, 7 to infinity, you can see where it splits. X minus 7 cannot equal 0. X cannot equal 7. There is our vertical asymptote. So where is it increasing? We saw from the graph, it's increasing in 2 different places. What was the next part? Can't remember the order which this thing asks. Determine the coordinates of the relative extrema. That would be where the derivative equals 0. It doesn't. Okay, it didn't switch. It's going positive, it stops, and it continues to go positive. So we never switch from negative to positive. So that's an interesting thing that can happen with rational functions. Determine the vertical asymptotes. That's really easy. X equals 7. No problem. Determine the horizontal asymptote. select the correct choice below. If necessary, fill in the answer. Well, what is this tending towards? If f of x equals -3 over x, it's going to 1 over x. That's our base case, 1 over x. So y equals 0. Y equals 0. Slant, well, no, that's not going to be the case. Slant is the case that we haven't worked with yet, and that's if the numerator is more than 1 of order than the denominator. Then we have to long divide, which is certainly not the case for this because we have the horizontal asymptote of 0. On what intervals is it concave up? On what intervals is it concave down? Let's look at the graph and see if we can just tell from a graph. Okay. So here, what does that look like? Looks kind of like concave up. Here, looks kind of like concave down to me. Up is a cup, down is a frown. Let's put that in interval notation. From -infinity to 7, up as a cup. From 7 to positive infinity, down as a frown. Now I can flip back to my homework. See that that has to be true. And is that some more questions? Determine the coordinates of the inflection point. It doesn't have an inflection point. We talked about that. Determine the x-intercepts. Well, it's asymptotic to y equals 0, so it will never have an x-intercept. And what are the y-intercepts? That's pretty easy to do, so let's do that. Y-intercept. There are a lot of questions to talk about y-intercept. Y-intercept, remember for a line, that's the b part. Where does that occur? When x equals 0. This implies that x equals 0. If x equals 0, plug it in. -3, 0 minus 7 is -3 over -7. Or is it -3? Positive 3, 7 is the point. So we'll see 0, 3 sevens. Is that all the questions? Oh, and then the last one was, what does the graph look like? But which you can use the graph calculator, and that's fine. It's pretty easy to pick out. This is why this homework took me so much more time, because of all those parts, right? So, look out for that. I'm warning you that it has all those parts, and it took me extra time, so it's probably going to take you extra time. I think the second one took me twice as long as the first one. I think it was about 2 hours of looking at it. Of course, I daydream and lose track of what I'm doing. Check my phone just like anybody else, but just a warning. All right, that's 12. Still want to talk about this slant. So 13, I can't remember. Loading. No, it's not 13. This is almost the exact same question we just did. And that's something I noticed about this homework too. As a matter of fact, I got the same question twice. Is it this one? But somewhere I actually got this. Let's talk about 14 instead. There was something interesting about this one that I noticed. I find that this one is a little easier in parts if I rearrange this. So I'm going to. This would be x squared plus 19 over x. I can rearrange that. I just multiply. It's just like doing think about the number 2 plus 1/2. Same idea. 2 times 2 is 4. Just a fraction thing. But sometimes it's easier to use it this way than to use it. But now I have both ways, so I should be good to go. So I thought I would mention it, especially with the asymptote, right? Because I have x squared over x, and that tells me I have 1 degree higher than the denominator, and that tells me about the asymptote. So I thought maybe I would mention it. On what interval is f increasing, decreasing, select? Okay, let's graph it and see what it looks like. X plus 19. Sorry for all the flipping, but that's the only way I know how to do it. Plus 19. You can see that those are the same function. Okay. On what interval is this increasing? Well, looks like it's increasing going this way from negative infinity to this number. What is that number? Negative 4.359. We'll have to talk about where we get that. But we see it's increasing there. Where else is it increasing? Certainly increasing over here. So from this number, I notice that's the positive version of that number. Or is it decreasing? From 0 and over here. Okay. So it turns out it's root 19, but where did I get that? So I need to go back. Sorry for the flipping. It's hard to do this virtually. Okay. We could take the derivative and set it equal to 0, right? And that would tell us where those points are. So f prime of x would equal 1. You know what? Just for funsies, I'm going to rewrite this another way once more. F of x equals x plus 19x to the negative first. That ought to do it. So the derivative then is f prime of x equals 1 negative 19x to the negative 2. Set that equal to 0. F prime of x equals 1 minus 19 over x squared. Set that equal to 0. 1 minus 19 over x squared equals 0. 1 equals 19 over x squared. X squared equals 19. X equals plus or minus root 19. Clear as mud, right? So how did I do that? Took the derivative. To do that, I introduced yet another way of writing this function. Take the derivative, set it equal to 0. Solve for x. That's where it occurs. So we see by graph and by actually finding that point where it's increasing and decreasing, and why we have so many different ways this is going to occur. Is that clear enough, you think? Yeah, okay. All right, what is the next part of the question? Next part says determine the coordinates. Well, that was fairly easy to do. Once I found my x equals plus or minus root 19, we can just plug that in to the original function. That equals. Now the asymptote. Oh, sorry, vertical asymptote. I was excited. Vertical asymptote is obviously x equals 0, because we can't divide by 0. It's not equal 0. There's your vertical asymptote. Hopefully the next part is horizontal. It does not have a vertical. Saying the wrong thing. It does not have a horizontal asymptote. Why? Why doesn't it have horizontal asymptote? F of x equals x squared plus 19 over x. The order of the numerator is one more than the denominator. So this is roughly just x. It's roughly y equals x. So roughly y equals x. And we say that doesn't have a horizontal asymptote. So that was one of the cases. Which case was that? 1, 2, or 3? There we go. Case 1. If the result has no variables and the denominator of the function has no horizontal asymptote. That's what we have here. Determine the slant asymptote. Select the correct choice. If necessary, fill in the box. All right, I kind of spilled the beans before. Let's do it again. I can rewrite this as x squared plus 19 over x. What is my ratio? X squared over x. X. So this is like y equals x when x goes to infinity. Let's look at our graph again. There's our graph. Horizontal asymptote, yeah, it is slanted. What is that slant? Y equals x. See there in the green. See the horizontal asymptote or the slant asymptote. You see it's never touching this line. Y equals x. That occurs when the order, the degree of the numerator is larger than the denominator. If it's just by 1, it's probably y equals x. And then I'll show you if it gets really ugly, or if it's in 2 orders or 3 orders, how do you find that slant asymptote? We'll go over that. It's in one of the questions. Those are a little bit more exciting. I want intervals that concave up and want intervals that concave down. Fairly easy to see if we have graph. See, from negative infinity to 0, it's concave down. From 0 to infinity, it's concave up, at least with my numbers. Determine the coordinates of the point of inflection. There are no inflection points. There are no x-intercepts. There are no y-intercepts. And choose the graph. Okay, so we don't even have to graph it ourselves. You just have to choose it, but there's there's 10 parts to that question, so it's almost like 10 questions. So that can suck up a lot of time. So
Just go back.
I'd be happy to. Which part?
Thank you.
First part, find increasing, decreasing. I did have to find those critical points to do that. Took the derivative, set it equal to 0, solved. And then I peeked at my graph while I knew what point it was, while peeking at the graph, and that's how I did it.
This thing's so weird. I had like the radical sign over the parentheses on accident. I thought, and I counted it.
Oh
And so I
yeah,
was
it can
like,
be
what
really,
did I miss?
it can be extraordinarily finicky. In fact, there was one I was gonna leave wrong, so I could talk about how finicky. The other point of contention.
Can you go over the second part?
Yeah. Let's look at number 15. Talk about what this has to say. Sketch the graph. Following function indicate where the function is increasing or decreasing, where any relative extrema or asymptotes occur. The graph is concave up or concave down, where any points of inflection occur and where the intercepts occur. All right, note for this, at least my numbers, that the numerator is larger than the denominator. And so that means we're not going to have a straight horizontal asymptote, but we probably are going to have a slant asymptote. So that's something to look out for. Okay. First part says on what intervals is f increasing or decreasing? Select the choice. So really we should take the derivative of this function, set it equal to 0, and find that. If we want, we can just use the graphing calculator to really help us along. I think that's how I'm going to do it, because I think that would be the most efficient for your time. So, with that, a lot of this has to do with visuals. So if you want to use a graphing calculator, you go wrong. So where is this function increasing? And where are its critical points? So we have 2, 4. Or 8, we need to talk about. Function is increasing, going from negative infinity up to 2, 4, or let's say up to 2. It's also increasing from 4 to infinity. So f of x is greater than 0, negative infinity to 2, and also from 4 to infinity. You see that? That's true. Where is it negative? Where is it decreasing? F prime of x is less than 0. Starting at negative 2, I'm sorry, positive 2, up to vertical asymptote, which looks like it's x equals 4. Sorry, x equals 3. Then from 3 to 4. Decreasing. So that's increasing, decreasing. We could take the derivative, set it equal to 0, plug in our points, do all that, but if we can use a graphic calculator as well, that's process up quite a bit. So the function is increasing from negative infinity to 2 and also from 4 to infinity. We saw that. It's decreasing from 2 to 3. 3 is our vertical asymptote and 3 to 4. So we see that must be true. Determine the coordinates or relative extrema. Well, we've already isolated that. The point 2, 4, and 4, 8 is where we saw that those occurred. It's fairly straightforward. Determine the vertical asymptote. That's very easy to do. We have x minus 3 that cannot equal 0, so x cannot equal 3. Vertical asymptote. Most interesting part is the horizontal asymptote. It says determine the horizontal asymptote. We don't have one because the degree of the numerator is larger than the denominator. So no horizontal asymptote for us on that one. Determine the slant asymptote. Let's look at this. What do we have? We have f of x, x squared, minus 8 over x minus 3. As x goes to infinity, or as x goes to negative infinity, the only thing that's going to matter are those orders. So you're really going towards x squared over x. You're going y equals x. Okay, but there's a bit of a slant to it. Where does that come up? It comes up because of the particular numbers we're dealing with. So that being the case, let's try to find where that occurs. It's possible in pre-calculus, we went over this. I know in my class we went over it a lot because the textbook made us. Let's long divide this function and see what happens. So do you remember long dividing polynomials? How many x's do I need to make x squared? Just x's, so I get x squared minus 3x. Subtract x squared minus x squared is 0. Negative 8 minus negative 3x is positive 3x minus 8. What do I need to multiply x by to get 3x? 3. 3x minus 9, subtract 0, negative 8, minus 9 is 1. So you get x plus 3. Okay. So x plus 3 must be the horizontal asymptote for this function. How did I do that? Just long divided the polynomials. Let me take a picture of that and shove this. Well, hopefully I can shove this up so we can look at that. Plus 3, that horizontal, oh, I'm sorry, the slanted asymptote. How do you find that? You just long divide polynomials. In the same way that you would long divide 7 over 5 to find decimal representation. Right? 5 into 7, how many times 5 go into 7? They can. Or just one time, I guess, right? Or 7 divided by 5, x squared minus 8 over x minus 3 is x plus 3 with a remainder. We don't care about the remainder. So you just have to long divide it like you did in pre-calculus. Save a picture of that. That was 15. I think there's a copy of it 16. We don't need to go over that right now. 320. This will be fine because we don't have to have slant. 18. No slant. Here, let's do the word problem. Those can be tricky. Cities and companies find that the cost of pollution control increases along the percentage of pollutants to be removed in a situation. Suppose that the cost C in dollars, then removing P% of pollutants from chemical spill is given below. Complete parts A through D. Okay, let's do it. Well, this is pretty easy. We just plug and chug, plug and chug. So that's all I did. C of 0 turned out to be 240. C of 15. C of 60. We're going to use these numbers in just a minute. 60, which is 40. 100. And C of 90. That's just 10. Go. All right, find the domain of C. We've talked about domain before, but let's talk about it again. Domain is the valid X values, what you're allowed to plug in for X. In this case, I guess it would be P. That's the idea, the input values. Well, what can it not be? 100 minus P cannot equal 0. So you can't plug anything that makes that happen. So I'd say P cannot equal 100. And in this case, since it's a real physical thing, P has to be greater than or equal to 0, since we're talking about real things. So for my numbers, it would be from 0 to 100, excluding 100. Plug that in your graphing calculator and see the function, but it's not too bad. And then the last part, it says, can the company or city remove 100% of pollutants due to the spill? No, as a percent pollutants approaches 100, the cost C approaches infinity, which is not important. We take an infinite amount of resources to get it down to 0. If you're studying to become a scientist or something like that, or a research scientist, you will run into that. Where is this possible? No, because we would need infinite amount of resources for this to occur. In case you ever study, the one I remember is, could we ever develop a machine that could create absolute 0, the temperature, absolute 0? You couldn't, because you would need infinite amount of resources, infinite amount of electricity, infinite amount of money to make the machine to do that. So sometimes you do that, especially in theoretical physics, which I studied a lot of my undergrad. You'll run into that. Okay, computations as well. Okay? Can you ever create a machine that is as intelligent as a human being? Well, maybe that would asymptotically go to infinity. Okay, so that's 19. What was one thing to talk about? I want to talk about the word problems. 23 bring us. Well, it's not a word problem, but we can talk about it. Find the absolute maximum, absolute minimum on a restricted domain. That's important to note. So this has a restricted domain. Okay. All right, with the restricted domain, that means the absolute maximum, absolute minimum could occur on the restricted domain, not just because of the derivative. So that's something to keep in mind. What's f prime? 2x minus 2, f prime equals 0, 2x minus 2 equals 0, x equals 1. So we have a critical point occurring at x equals 1. Here. What is f1 squared minus 2 times 1 minus 2? 1 minus 2, negative 1, so it's negative 3. Negative 3. That could be the minimum, that could be the maximum, or it could just be a relative min or max, because we have a restricted domain. So we need to also check what's going on at f of 0, what's going on at f of 5. So because this is restricted domain, the max or min could lie there as well. So for my numbers, f of 0 will just be negative 2. F of 5 would be 5 squared minus 2 times 5, which is 10, minus 2, so that's 15 minus 2, which is 13. Okay, so the min or max, absolute min and max for the function could exist there. So what is the absolute maximum value? For mine, it occurred at 13. You see that that's true, that's occurring at x equals 5. Okay, that's because the domain was bounded. The absolute min or max for this, well, I found it was negative 3, which I found by taking the derivative set that equals 0. There's possibility that in certain examples that would only be a relative min or max. With the restricted domains, you have to check both the critical points and the restricted boundaries. Okay, so keep that in mind. I remember my teacher telling me that. I don't think I had a clue what he was talking about when he told me, but now that I'm in the hot seat, I remember him saying it. So find the absolute maximum and minimum values of each function over the indicated interval, indicate the x values at which they occur. So let's do that. What is f prime of x? I'll move that here. As long as the stupid computer won't minimize the window for that reason. Prime of x would be 9x minus 6x minus 3. Okay, set that equal to 0. F prime of x equals 0. X squared minus 6x minus 3 equals 0. If we like, we could try to use the AC method. Or we could just use the quadratic formula. It's like 3 and 9 would do it. Minus 6x 3 equals 0. 9x squared minus 9x plus 3x minus 3 equals 0. 9x x minus 1 plus 3 x minus 1 equals 0. X minus 1, 9x plus 3 equals 0. X equals 1, or 9x plus 3 equals 0. X equals negative 1/3. All right. Or you can use quadratic formula or AC method, however you take it. So it looks like we have something going on at -1/3 and something going on at x equals 1. Note, for my numbers, x equals 1 is not in the domain, so I'm gonna get rid of that one. Don't need that one. Okay, so that means we need to plug this in. F of -1/3 equals 3, -1/3, minus 3, -1/3, minus 3, -1/3, plus 2. 3 over -1/27 minus 3 over 9 minus 3 over 3 plus 2, 23/9. So that's going on to critical point. We also need to check at these boundary points. So we need to also check f of -1, f of 0. Need to check those. Right. Seems like I wanted to say something about 27. An employee's monthly production M and number of units produced is found to be the function of the number T years of service. For a certain product, productivity function is shown below. Find the maximum productivity and the year in which it was achieved. So if you want to find max, I would take the derivative and set it equal to 0. Seems like a good place to start. So m prime of t equal -8t plus 184. M prime of t equals 0 gives me -8t plus 184 equals 0. So t equals -184 divided by -8, or 3. So that's where I find t equals, they told me that this is occurring in days. T is in days. Nope. T is in years, excuse me. T is in years, so 23 years. M of 23 is -423 squared plus 184, 23 plus 110 equals 2,226 units. Take the derivative, set it equal to 0, solve for t, plug that t into your function. Next question. For a dosage of x cubic centimeters, cc's of a certain drug, the resulting blood pressure B and approximated by the function below. Find the maximum blood pressure dosage which this occurs. All right, same idea, different problem. Let's find the derivative. Times 2, 790 x minus 740 times 3. My function. Now I want to set my derivative equal to 0. Divide both sides by x, but x cannot equal 0. After that, just plug that number into the original function. Don't forget to round appropriately. What did we learn? We learned if you take the derivative, set it equal to 0, this tells you where the slope is 0, and that must be a turning point, a critical point. When you do that, you have found either the minimum or maximum, could be relative, could be maximum, absolute. But from there, you can tell that the derivative is changing from negative to positive or positive to negative. One of the cornerstones of Calculus 1 is doing this. So this is really important. I tried to highlight the critical, unintended, the critical points of the lecture. But yeah, there was low attendance, so I'm not going to stop for questions because nobody's here. So I wish you well. I know that the midterm is due today, so that's probably the cause. Please email me if you have any further questions. And I wish you well. I will see you next week.